Hi, everyone. Welcome to the Temporal Graph Reading Group today. Um, we are glad to have Haonan here, who will present their recent work, Dynamic Graph Information Bottleneck. And Haonan Yuan is currently a PhD candidate at the State Key Lab of Software Development Environment and Beijing Advanced Innovation Center for Big Data and Brain Computing at um, Beihang University and supervised by Prof. Jianxing Li and Prof. Qianyun Sun. His research interests include generalizable graph representation learning, dynamic graph learning, and graph foundational model. His work has been published in top-tier conferences in the field, such as New York's AAAI, the Web Conference, and CIKM. And he is also the program committee member of the Graph Foundational Model Workshop for the Web Conference 2024 in Singapore. And I will hand the mic to you, Haonan.
Okay, can everyone hear me? Yeah. So
yes,
thanks
we can
for
hear you.
okay, thanks for Andy's introduction, and it's really a great honor for me to be invited here to present my work in a temporal graph reading group. And now I'd like to introduce my work named Dynamic Graph Information Bottleneck, or we call it DGIB, which is accepted in the Web Conference 2024 of the research track. And I will also present this work during a web conference meeting on May the 15th in Singapore. So you can scan the 3 QR codes to get the paper, code, or datasets and reach out to my Google Scholar homepage. And on behalf of all my co-authors, we sincerely and kindly welcome your citations and stars. So, okay, now let me begin my introduction. And as is known to all, the graphs, or we say the network structures, are everywhere in the real-world scenarios or in a cyberspace. For example, the social web network describes the relations between friends, the relations between celebrities and their fans. The biology network represents the complex interactive patterns between genes, molecules, or the proteins. And additionally, over time, the static graph takes on the property of a time dimension and becomes the dynamic graph. For example, the traffic network describes the traffic flow of the urban transport network at different times of the day. And the transaction network describes the trading relations between clients, banks, and companies on different days. So before diving further into the implications of graph dynamics, I want to first clarify some conceptions from my perspective about the dynamic graphs and the temporal graphs. So the dynamic graph and the temporal graphs, I think, are two concepts in the graph theory that differs in how they deal with dynamics changes in graphs. The dynamic graph is a graph in which the structure of the graph, for example, the nodes and edges changes over time. So in dynamic graphs, the focus is usually on the process of changing the graph, such as adding or removing the nodes, edges, and updating nodes and edge properties. And dynamic graphs can be used to simulate changes in interpersonal relations in social networks and the traffic flows in the traffic networks, etc. However, the temporal graph, I think, is somewhat a special kind of dynamic graph that focuses not only on the structural changes in the graph, but also the exact point in time at which those changes occur. So in a temporal graph, each edge or node is associated with a specific time step and indicating that the edge or nodes exist or changes at that point in time. And temporal graphs are suitable for scenarios that require accurate time information, such as the delivery time of message in a communication network or the time series of transactions in the stock market. So the analysis of temporal graph usually involves time series analysis and the time dependence modeling, and etc. So in summary, the main difference between the two graphs lies in the processing of time information. The dynamic graph focuses more changes in the graph structure, while the temporal graph adds considerations of more fine-grained temporal changes. So our work focuses more on the dynamic graphs. So this is the aforementioned clarifications I want to explain. And so let's continue.
So there's a question. Do you prefer to have question now or at the end of the talk?
Anytime you can just interrupt me for a question.
Okay, so there's a question in the chat. So going back to your definition, can we say every dynamic graph is temporal graph, but the reverse is not true?
Yes, I think the dynamic graphs, the temporal graph is more complicated. Yeah, it's described the continuous time changes in the graph, but dynamic graphs is more like discrete graph snapshots, those time slices.
Oh, I see. So yeah. So basically, what you mean by dynamic graph are snapshot-based graph, like temporal graph, and then what we call continuous time dynamic graph is what you call temporal graph. Yes.
Pardon, can you repeat again? Sorry.
So just to clarify a little bit, so the dynamic graph that you mean are snapshot based, right? So you have daily graph, and each graph is basically a different snapshot.
Yeah. Yes.
And then temporal graph, in your definition, is basically continuous time dynamic graph, which is you have edges arriving in a stream.
Yeah, I think so.
Okay, so I think we're okay. Yeah, thanks for the clarification.
Yeah, our work is focused more on the discrete dynamic graph.
I see.
Okay. Yeah. So let me continue. So okay. As is accepted by is a well-known scenario that the powerful GNs are susceptible to potential adversarial attacks. Let's see the example of the node classification task. We have an attacker node and the target node to be attacked. However, we don't need to directly attack the target node, as a message passing mechanism in most GNs enables nodes on the graph to, for example, merge, fuse, or update information from the neighbor nodes. We only need to perform some small perturbations on the features or structures of the attacker nodes that can lead to misclassifications of the target. We call this attacking mode as the influence attack, which can better hide the attackers. So taking the real graph data, for example, we perform both direct and influence attack on static data, and the results demonstrate again that the small perturbations can lead to sharp decrease in the mode performance. And taking back to the dynamic graphs within our scope, the spatial temporal correlations in dynamic graph is more complex and coupled. And the dynamic GNs will be more sensitive to random noise and potential targeted adversarial attacks. So our question is, what is a good representation for graphs? Here we would like to introduce some conceptions of the information bottleneck first. The information bottleneck method is a technique in the information theory. It is designed for finding the best trade-off between accuracy and complexity, or we say the compression, when summarizing a random variable, for example, the x, given a joint probability distribution Txy. And the observed relevant variable, y. The information bottleneck self-described as providing a surprisingly rich framework for discussing a variety of problems in signal processing and learning. So here we illustrate an example in a task of image classification, which aims to judge whether the picture is a cat or a kangaroo. So the green part is a task relevant part, and the orange part is the task irrelevant part. So the information bottleneck aims to encourage the feature extractor to abandon the redundant features and conserve the task-relevant features, and encourages the classifier to rely on the task-relevant features to make predictions. As the task-relevant features are invariant, this leads to a more robust model performance. The existing IB works can be categorized into 3 typical types. For example, we first introduced the vanilla IB. The vanilla IB objective is to maximize the objectives. Here, the I function means the mutual information. The mutual information of the 2 variables is a measurement of the mutual dependence between the 2 variables. For example, here, the IZY measures the mutual information between the latent representation Y and the label latent representation Z and the label Y. So more specifically, it quantifies the amount of information in units such as the channel beats, nets, or hat layers obtained about 1 random variables by observing the other random variable. We can see from the Venn charts, the goal of the IB is to find the optimal latent representation Z. This is a 2-stage process. The first stage, known as the noise or irrelevant information compression stage, is to minimize the mutual information between the input X and the intermediate variable Z. And the second stage, known as the relevant information conservation stage, is to maximize the mutual information between the intermediate variable Z and the target label Y. This is a process of mutual conditioning, and eventually a balance between the 2 stages is reached. That is, the intermediate variable Z retains as much information as possible between the target Y and the input, while retaining as little information as possible. So this is the most traditional IB theory. And when it comes to the scenario of graphs, we call it graph IB or GIB. And GIB can be further categorized into the non-structure involved GIB and the structure involved GIB. The non-structure involved GIB aims to find a subgraph. We call it IB graph that can act as the same role as the intermediate representation Z does in the vanilla IB. So it also follows the 2-stage optimization process. However, it is difficult to calculate the value of the mutual information directly because the non-Euclidean feature of the graph data. It's really hard to directly compute between the graph structure data and the vector embedding. So therefore, this method usually transforms the graphs into the embedding and uses the vanilla IB to calculate the mutual information between vectors so that this optimization goal can be tractable and feasible in the gradient backpropagation process. As an important feature of the graph structure, it's not directly involved in the calculation and optimization process. So this non-structure involved GIB, the performance is not so outstanding. The third type of IB is the structure directly involved IB, in which the graph structure is directly involved in the IB calculation and optimization process. And the most typical work is the GIB published in the NeurIPS 2020 by Tailing Wu. And this GIB divides the graph data input into 2 parts, the feature parts and the structure part, and let the structure directly participate in the calculation and the optimization process of the IB theory, and adopt a series of approximate methods and make it possible to calculate the mutual information and make it feasible to training. And it can make it the calculate the mutual information of the non-graph data directly. So in summary, all the 3 types of the IB models can be represented by the following 3 Venn diagram. So the analysis of the existing work indicate that the existing GNNs are highly sensitive to counterattacks because the information that is not relevant to the task objective is encoded into the latent representation. So using the information bottleneck as the optimization goal to constrain the learning behavior of GNNs can make the learned graph representation contain the minimal and sufficient information and can achieve a good prediction. So let's make the question further. What is a good representation for dynamic graphs? And to test whether the minimal and sufficient graph representation on the static graph is also a good representation in dynamic scenarios, we do a case study. The setup of this experiment is as follows. We directly apply the DGIB used for static graphs to the dynamic scenarios and test the performance of the link prediction task. The dynamic data set adopter has a time granularity of days. The first 20 days of data are used for training, and the last 10 days of data are used for a verification test. So from the results, we have a noteworthy finding, is that the prediction performance for the next time step graph during the training significantly surpasses that for the target graph during the validation and testing stages. So this shows that directly adapting GIB can better capture the spatial temporal correlation between data in the training stage, and make better predictions about the link prediction in the next time slice. However, due to the unknown, maybe the potential distribution shifts of the verification or the test data, the minimal and sufficient information learned by the model in the training stage changes. So resulting in rapid decline in the accuracy of the connection in the link prediction task. And so in our work, we propose that a good dynamic graph representation should meet the MSC condition of the minimal, sufficient, and consensual. So how to implement the MSC condition is an unknown challenge in the field of dynamic graph learning. We face three main challenges. The first is how to understand what constitutes the optimal representation that is both discriminative and robust for downstream task prediction under the dynamic scenario, and how to appropriately compress the input features by optimizing the information flow across graph snapshots with structures straightforwardly involved. And the third challenge is how to optimize the intractable IB objectives, which are incalculable on the non-Euclidean dynamic graphs. So considering the most challenging task on the dynamic graph learning, we first give some assumptions of the MSA condition on the link prediction task. So given a dynamic graph DG and the optimal representation at the time t+1 is the Z for the robust future link prediction should satisfy the MSA condition such that we minimize the mutual information between SD and D, which is under these constraints to find the later representation Z at time t+1, and where D is the input training data containing previous graphs G from time 1 to T, and the node feature X at time t+1, and the S function is some partitions of the input data D, which is implemented by a stochastic encoder P. And the P has some conditions where the C function satisfies the consensual constraint. So in simple terms, we first, this assumption declares that we first need to optimize the S function and find a way to partition the input information so that the mutual information between SD and the label Y is equivalent to the mutual information between the original input D and the label. So on this premise, minimizing the amount of information obtained from D in SD. So assumption 1 declares the optimal representation for the robust future link prediction task of dynamic graphs should be minimal, sufficient, and consensual. And among them, the minimal and sufficient concepts have been clearly understood in the previous introduction. So how to understand the consensual? We think that a consensual condition is like a button in the process of feature compression and guiding the optimization of information bottleneck in each time slice from a more global perspective. So looking back to the case study, we attribute the counterfactual results to the laziness of the deep neural networks and leading to the non-consensual feature compression for each time step. So the global representation does not always align with the minimal and sufficient assumption. So to encourage, we learn the best graph representation to reach the global minimum and sufficient status. The additional consensual constraint C is being applied to encourage the optimization process. So specifically here we illustrate the DGIB principle and the formal definition of our optimization goal. And also given the dynamic graph and the no features at the next time step, the DGIB objective is to learn the optimal representation Z at time t+1 that satisfies the MSA condition. By minimizing the DGIB objective, which is under the constraints of the stochastic encoder P, where the C theta condition is used to constrain the consensual assumption. So DGIB objective describe the dynamic graph information bottleneck instantiated by two terms. The first term is called the conservation term, which aims to maximize the mutual information between the latent representation Z and the label Y. And the second term is called the compression term, which aims to minimize the mutual information between the input data D and the latent representation Z. The two terms are balanced by the hyperparameter beta. And the overall goal of DGIB is to find a good dynamic graph representation Z that has satisfied the MSA condition, as well as lead to a good prediction performance. So as the most common, but also the most challenging problem in the graph information bottleneck, that is how to implement and optimize the DGIB objective, as the two mutual information terms are not directly tractable for the non-Euclidean dynamic graphs. And we propose a novel solution is to decompose the overall DGIB objective into two channels. That is the DGIB MS channel and the DGIB C channel. Here we should notice that when decomposing the overall training target into separate ones, we should guarantee that the parameter searching place, that is the omega here, the parameter searching space has also been decomposed. So the DGIB MS channel optimized the Z t+1 under the constraints of P conditioned by D and theta. And the DGIB MS channel guarantees the learned Z satisfied the minimal and sufficient assumption. And the second DGIB C channel encourages Z from 1 to T and Z at T share the consensual predictive patterns for predicting the final Y under the constraint of P, conditioned by Z from 1 to T and the C theta, where the C theta constraint is the consensual condition acting on the parameter searching place of P. So the two channels are jointly to satisfy the overall MSA condition and the final DGIB target. The overall DGIB framework first receives the dynamic graph data as input and then use the relative temporal encoding module to embed time features coding into each graph node in each time slice. So next, feature compression is carried out along the time dimension and space dimension respectively from two perspectives of node features and graph structure. So taking the time from t-1 to t, for example, the node features are updated through the message passing across time slices. In terms of the graph structure, the modulation, or we say compression of information flow across time can be realized by adjusting the weights of the edges and within the graph and across the time slice. So this process iteratively compresses structures and node features between graphs. And the DGIB MS channel and DGIB C channel as the optimization targets respectively guide the above information compression and the retention process from the two dimensions of first is the minimum and sufficient, and the second is the consensual, and finally get the ZT+1 through the information bottleneck. Next, we introduce how to calculate and optimize the target of the two channels respectively. So first, for the DGIBMS, directly optimizing this channel poses a significant challenge due to the complex spatial temporal correlations. And the IID, the independent and identical distribution assumption, typically is necessary for estimating the variational bounds for those mutual informations. And the IID assumption is a key factor in rendering the optimization of the IB objectives feasible. However, the IID assumption cannot be reached in dynamic graphs as the node features exhibit correlations owing to the underlying graph structures and the dependencies are intricate. So to solve the above challenges, we propose the spatial temporal local dependence assumption. Given the dynamic graph, and let the NST be the spatial temporal k-hop neighbors of any node V, and the rest of the whole dynamic graphs will be independent of this node and its spatial temporal k-hop neighbors. So in short, for a given dynamic graph, if any node V is specified, the embedding of this node is only related to the k-hop neighbors of the node in the current time t and the k-hop neighbors of the previous time, and is completely irrelevant to the other parts of this dynamic graph. So this assumption is applied to constrain the search space omega as the P, which leads to a more feasible DGIB MS channel.
Can I ask a question?
Okay.
Yeah, so basically you are doing the like the Markov assumption here, right? So you're assuming the current time is only dependent on t-1. And what if you have any graph dynamics that are, that are in sequence, like spanning over 5 or 6 snapshots, for example? Then it will not be modeled by this.
Okay, I got your meaning. We reckon that this assumption is kind of simple. Yeah, the situation you described is actually exists in the real graph data sets or dynamic graph scenarios. But if we decompose the whole dynamic graph into some pairs, so we only cares about the two graph snapshots within this series. And we think the most influential part is the graph snapshot at time t and the previous time at t-1. So it can decide the most influential part of those graph data. So we just omit the more previous ones.
Okay. So this is basically one like implementation choice, basically.
Yeah, it's we have to make such assumptions to make our implementations feasible.
Okay.
It's a kind of approximation method.
I see. Okay, thank you.
Okay, let me continue. So we can now give the formal definition of the optimization goal for the DGIB MS channel. We find that the optimization goal of this channel still follows the expression form of the IB in the mathematical expression form. So maximizing the mutual information between the intermediate variable Z and the label Y, and minimizing the mutual information between the input data D and the intermediate variable Z, respectively. So in order to make the two mutual informations in expression computable and feasible, we propose the upper and lower bounds respectively. So in order to maximize the mutual information of the first term, we can give the definite expression for the lower bound of the mutual information and indirectly maximize the first term itself by maximizing the determined lower bound. Similarly, in order to minimize the mutual information of the second term, we can give an upper bound for the mutual information, which indirectly minimize the second term in itself by minimizing the determined upper bound. So what follows is some details and in-depth mathematical derivation showing how we can shrink or transform this upper and lower bounds into expressions that can be directly computed or optimized. For example, for the lower bound of this mutual information, as the training progresses, the first half of this will converge to a constant, so it can be ignored. And the rest part, it turns out, converges to the cross entropy between these two items. And the upper bound of the mutual information can be calculated by means of distributed sampling and the variational approximation. According to different methods of distribution sampling, two different approximate methods can be used here, namely the Bernoulli distribution sampling and the categorical distribution sampling. Similarly, we define the optimization goals for the DGIB-C channel, and similar to the DGIB-MS channel, the expression form structure of this channel is similar to the IB structure, and is maximizing and minimizing two mutual information items respectively. We also propose the lower and upper bounds for the optimization objectives of the two mutual information items. Similarly, the first half of the lower bound converges to a constant in training and can be ignored, and the rest part converges to the cross entropy. And the upper bound of this mutual information can be the prior approximation to the multivariate Gaussian distribution. So in summary, the optimization goal for the for the MS channel is to find the minimal and sufficient intermediate variable ZT+1, while the optimization goal for the DGIB-C channel was to encourage the semantic consistency or consensual between the intermediate variable Z from 1 to T in each time slice and the final representation ZT+1. The two optimization objectives are merged into the overall optimization objective through the trade-off by the hyperparameter alpha, and the dynamic graph representation finally meeting the minimal, sufficient, and consensual conditions is optimized under the joint efforts of the two channels, thus achieving better prediction performance on the downstream task. This is the overall training pipeline of the DGIB framework. We have analyzed the computational complexity and this in our paper, which can be specifically reviewed in the corresponding chapters in the appendix. So the analysis concluded that the computational complexity is on par with the state-of-the-art dynamic GNS. Next, I will introduce the experiment settings. So in order to comprehensively evaluate the effectiveness of our proposed method, we use 3 real-world dynamic graph datasets to evaluate on the challenging future link prediction task. So the CoLab is an academic collaboration dataset with papers published in 16 years, which reviews the dynamic citation networks among others. And the Yelp contains customer reviews on business for 24 months, which are collected from the crowdsourced local business review and social networking web. And the ACT describes the actions taken by users on a popular MOOC website within 30 days, and each action has a binary label. So the statistics of this dataset are concluded in a table, which also contains the split of the snapshot for training, validation, and testing. And we compare our DGIB with 3 groups of baselines that is static GNs, including GAE, VGAE, and GAT, and dynamic GNs, including GCRN, evolve GCN, and DYSAT. And the third group is robust DGNs and regularizers, including IRM, VREX, Group DRO, RGCN, DIDA, and the pioneering work GIB. So we compare baselines and propose the DGIB on the two adversarial attack settings. The first setting is the non-targeted adversarial attack. We produce some synthetic datasets by attacking graph structures and node features respectively. For structures, we randomly remove links, and for node features, we randomly add some noise. The second setting is the targeted adversarial attack. We apply the prevailing NetTag library. This is a strong targeted adversarial attack library on graphs designed to target nodes by altering their connection edges and node features. We simultaneously consider the evasion attack and the poisoning attack. The evasion attack, we train the model on the clean datasets and perform attacking on each graph snapshot in the testing split. And for the poisoning attack, we attack the whole dataset before the model training and testing. So in both scenarios, we follow the default settings of the NetTag to select the target attack nodes and choose GAT as a surrogate model with default parameter setting. First, we evaluate model performance on the future link prediction task, as well as the robustness against the non-targeted adversarial attacks in terms of the graph structures and node features. So specifically, we train baselines and our DGIB on the clean datasets, after which we perturb edges and features respectively on the testing split following the experimental settings. And the results are reported with the metric of the AUC score in 5 rounds and concluded in this table. So we can find that the DGIB burn, which means the Bernoulli distribution sampling, and the DGIB Kate means the categorical sampling, outperforms the GIB and other baselines in most scenarios. The static GNs baselines fail in all settings as they cannot model dynamics. And the dynamic GN baselines fails due to their weak robustness. Some robust and generalized DGNs, such as the group DRO, DIDA, and GIB outperforms DGIB burn or DGIB cat slightly in a few scenarios, but they generally fall behind the DGIB in most cases due to the insufficient feature compression and conservation, which greatly impact the model robustness against the non-targeted adversarial attacks. And we continue to compare the proposed method with the competitive baselines standing out in table 1. So considering the link prediction performance and robustness against the targeted adversarial attacks, which reviews whether we successfully defended the attacks. So specifically, we generate attacked datasets with the NetTag as introduced before, and concerning different permutation times n in both the evasion and the poisoning attacking mode. So higher n represents a heavier attacking degree. Results are reported in this table. And we can find that the DGIB burn and DGIB Kate outperforms all baselines under different settings. Results demonstrate that our DGIB is contained under challenging evasion and poisoning adversarial attacks. And comprehensively, the DGIB burn owns a better performance in targeted adversarial attacks with a lower average AUC decrease, while the DGIB burn is better in the non-targeted adversarial attacks. So we explain this phenomenon as the categorical distribution is a non-informative distribution, which fits well to the non-targeted settings, and the Bernoulli distribution requires some priors, which may be more appropriate for against the targeted attacks. And in the ablation study, we analyzed the effectiveness of the 3 variants. Firstly, the DGIB with accounts, we remove the consensual channel DGIBC in the overall training objective and optimizing only with the DGIB MS channel. And the second variant is the DGIB without A. That means we remove the structure sampling term in the upper bound. And the third variant is the DGIB without Z. We remove the feature sampling term in the upper bound of this mutual information. So from the result, we can see that overall DGIB outperforms the other three variants except for the DGIB without A, where it exceeds in the original DGIB burn on the clean collab by about 1%. So we claim this phenomenon is within our expectation, as the structure sampling term A contributes to raising the robustness by refining structures and compression feature information, which will surely damage the performance on the clean datasets. And concretely, we witness the DGIB surpassing all the three variants when confronting evasion and poisoning adversarial attacks, which provides insights into the effectiveness of the proposed components and demonstrates their importance in achieving better performance for robust representation learning on dynamic graphs. So next, we carried out the information plane analysis. The information plane is widely applied to analyze the changes in the mutual information between the input latent representations and the output during training. So given the Markov chain x to y to z, the latent representation is uniquely mapped to a point in an information plane, which coordinates the I xz and the I yz. So theoretically, the optimization process of the information bottleneck should show a significant two-stage feature. If the expected two-stage feature appears in the experiment results, it shows that the information bottleneck is useful to guide the model learning the feature compression process and indicate that the approximate estimation method of the mutual information is correct. And we analyze the DGIB burned on the clean collab and we draw the coordinates. So from the results, we can see that the information evolution process is composed of the two phases. During the phase one, we call it the empirical risk minimization phase. The two axes, the coordinates on the two axes both increase. So indicating the latent representation are extracting information about the input and labels, and the coordinates are shifting towards the upper right corner. And in the phase two, we call it compression phase. The x coordinate means the IDZ. This value begins to decline while the growth rate of the y-axis slows down and converging to the upper left corner. So indicating our DGIB begins to take effect, leading to a minimal and sufficient latent representations with the consensual constraints. Next, we perform the hyperparameter analysis. We first analyze the sensitivity of the hyperparameter alpha, beta 1, and beta 2. So the results demonstrate that the performance on both the clean and the structure attacked collab is sensitive to different values of alpha or beta 1 and beta 2, and it contains in a reasonable range. In addition, we observe there exists the negative correlations between the performance on the clean datasets and the attacked datasets for all the three hyperparameters, which demonstrate that the confrontations of the MSE term and the compression term in the DGIB overall optimization objectives. And specifically, in most cases, the higher alpha or higher beta 1, higher beta 2 lead to better robustness but weaker clean dataset performance. So in conclusion, different combinations of the hyperparameters lead to a varying task performance and model robustness. And we follow the tradition of configuring the values of the three hyperparameters with the best trade-off setting against the adversarial attack. We then analyze the impact of the compression parameter beta 1 and beta 2 on the trade-off between the performance of prediction and robustness. We conduct experiments based on the DGIB burn with different ratios of the MSE term and compression term on the clean, evasion attacked, and the poisoning attacked collab respectively. We can see from the result that with the increase of the 1 over beta 1 or 1 over the beta 2, the DGIB burn performs better on the clean collab, while its robustness against the targeted adversarial attacks decreases. This validates the conflict between the MSE term and the compression term, as the compression term sacrifices prediction performance to improve the robustness, and we find the optimal setting for the both two hyperparameters where the performance of prediction and robustness are both real preserved. So last, we draw some conclusions of this work. We propose a novel DGIB framework for robust dynamic graph representation learning. To the best of our knowledge, this is the first exploration to extend the information bottleneck on the dynamic scenarios with structures directly involved in the IB optimization. And we investigated a new insight and proposed the MSA condition, which can be satisfied by the cooperation of both channels to refine the spatial temporal information flow for feature compression. And we further introduced their variational bounds for optimization. And the extensive experiments on both the real-world datasets demonstrate the superior robustness of our DGIB against the targeted and the non-targeted adversarial attacks compared with the state-of-the-art baselines. So in the future, there are some ideas or directions for us to try. The first is we extend the DGIB to more downstream graph tasks, such as the node classification or the graph classification, etc., and adapt the DGIB to the continuous dynamic graph scenarios for wider applications, such as the in-time traffic prediction or the anomaly detections, etc., and investigate the possibility of combining DGIB with the up-to-date GM backbones and architectures, such as graph transformers, and explore more efficiently estimated IB variational bounds to decrease the computational complexity, and construct a uniform framework to handle both static and dynamic graph robust representation learning. So thanks for your attention, and any questions?
Yeah, thanks for the great talk. So there are questions. Okay, yeah. So there's a question from the audience. So I will just read it here, or if you want to ask it yourself, you can feel free to like unmute and talk as well. Okay, so I will just read the message then. So thank you for your time on this paper. Very informative. I was wondering what were the timelines for this paper. So how much time it took you from getting the idea for the project until your final submission? Thank you.
Okay, thanks. Actually, this paper from the idea and the final submission is about 3 months. Because before this paper, we have completed a paper about the out of distribution generalization on the dynamic graphs, which is accepted by the NeurIPS 2023. So from doing that work, we find that the distribution shifts between the training and testing really decrease the model performance. And that work, we proposed some perspective from the environment learning and then from some causal inferences, and we train a more robust model. And however, we see that from the case study, we see that there still is a sharp decrease about the performance between the training and the testing. And we wonder if there is some things from this information theory perspective. And our group has have many works about the information bottleneck and some information analysis. So we want to explore whether we can solve the robustness or the generalizability of the GNs from this perspective. And you can see that the framework of this method is quite simple. There is not very much designs to the framework itself, but it's more about the derivation of the series or some calculations. So I think this is not a typical deep learning work in this field, and I think it's 3 months. We have the experiment is also very fast, and we have completed all the experiments and analyze the results. So 3 months, I think, is not so long for this paper to complete, but it is based on many previous works or foundations of our research group.
Mm-hmm. Yeah, so thanks so much for the for the very nice presentation. So I do have two quick questions. So first one is that as future work, you mentioned you want to like extend this to continuous time dynamic graph. And how do you think you propose to do that? Because currently the framework work with like snapshots, so you need to define the snapshots in some way first, right?
The most easy way, I think, to adapt this to a continuous scenario is use some sampling techniques. I think is in a continuous dynamic graph, not every time the graph is the importance varies. So not every time step the information contains in that time slices uh, is as much important as I have to take it for uh, uh, optimization. So I think the most easy way is to do some sampling strategies to select some pieces of the graph snapshot from the continuous part, and to can easily adapt the DGIB to the continuous scenarios. And about how you ask me how to step further, I have no more ideas. As I'm not very similar to the continuous scenarios, those methods or the models we haven't explored in that directions much.
Okay.
So that's a really
Yeah.
interesting question.
Yeah, sounds good. So I think it's very interesting, and this work definitely have both the theoretical flavor and the empirical like results to back it up. So I think it's a very nice work. One final just clarification question. So in the objective, when you talk about like for each node, how it's implemented, it seems to be like the node has to be exist for both snapshot, the t-1 and the t, in order for it to work. So how do you deal with nodes that are only in one of them, like or just show up?
Okay. Sorry. This is my. I don't explain it very clearly. So in the discrete dynamic graph learning, we always assume the nodes appears in every graph snapshot in a series. So this is the assumption. We always we always assume that nodes appears in every graph snapshot.
Okay, so by definition, this is also transductive, right? So you can only predict for nodes that you see during training, but not for new nodes because there's no new nodes
Yeah.
coming in. Okay.
Yeah.
I see.
Yeah, it's
Yes.
really a limitation.
Okay, sounds good. Yeah. Yes. So thanks for sharing the work again and the nice presentation. If you would like to share the slides and so on, I can also put it on the website. And yeah, so thanks everyone for coming to the talk, and I will see you next week for the next reading group. Thanks everyone. Yeah. And thanks
Bye-bye.
for the
Thanks.
presentation again. Yeah. Thanks.
Okay, thanks, Andy. Bye-bye.
Thank you. Bye.